Okay, well, thank you very much. It's both a pleasure and an honor to be invited to this conference. I've known, of course, all three honorees for a long time. First of all, Lisa and Jonathan, through that lovely paper of theirs on the SU2 connections on a Riemann surface, where they get this almost toric structure that's been a source of puzzlement for a long time for me. Then, of course, Lisa as both a collaborator and all too briefly a colleague at McGill. And of course, latterly as an admirer of, well, Jonathan, Yael, and Lisa, both for their wonderful work and for Yael and Lisa being at the heart of what has been, and I hope continues to be, a truly wonderful geometry group at the University of Toronto. So, congratulations. You've done well, and happy birthday. Also to those online. So, I'm talking about a subject it's the symplectic aspects are just sort of a vague memory by the time you get to this, but it's linked to the KP equations, and in the sort of 1970s, 1980s, the discovery of sort of integrable, what they call integrable, it's infinite dimensional, but anyway, Hamiltonian structures for the KdV, for the KP equation, sort of led to a whole revival of the subject of integrable systems. So what I'm talking now is basically a discrete version linked to some interesting and apparently very applicable lattice recursions. So let's see if this works. Okay, so there's some lattice recursions, and the ones I'm talking about are on Z3. And the first one is this Hirota recurrence. So I'll explain what these symbols mean. Well, I have there, but basically, they seem to occur in all sorts of fun places. So you can think of things, sort of models that are basically like the Ising model. So I'm quoting a paper of Kenyon and Pimentel because they've got the most complicated recurrences coming soon. But in their paper, they say, yeah, but well, under the name of Charles Dodgson, some identities for computing determinants occur in the 19th century. So what this means is you have a lattice in Z3, and of course it's giving you little cubes. So let's see if I can draw cubes. That's sort of cube-like. That'll do. There we go. So you're in the, take any point in the lattice and call it your origin, basically, and then you can shift by one that way. You can shift by one this way. You can shift by one that way, and if you do two shifts, you've got A1, 2, and so on. So what this is doing, and when you think of it as a recurrence, is you notice that the A term is not there, so you're taking basically these terms and dropping one, basically, and getting the remaining one. And the basic idea is that you're going out sort of transverse to this. So you have sort of nested egg crates, and they're sort of moving out. And so that's a recurrence. So this one seems to be linked to the A series of Lie groups. There's a cube recurrence due to Miwa, which I think occurs in more than this, perhaps a little bit obscure edition, but this seems to be the first one according to Kenyon and P. Mantle, where it's again the same notation, but this time you're computing the thing that's out here in terms of what's coming before. Then you see life gets more and more complicated. So these recurrences, Kashayev, which come up, and then this in this paper, where they're doing the sort of statistical mechanics of it and getting these sort of limiting shapes and things like this. Where now the recurrence involves let's see, not only quantities on the vertices, so as before, but quantities on the faces. So you take the face opposite to the z direction, and here you've got, well, I think I had h's there, but there'll be a's here, but this is a x. X? Superscript, okay. And so on, so this will be a y, and so on. Okay, and it's the same idea. You sort of advance diagonally and compute recursions. So what are these things? So there are various statements and various things in papers, and they often linking it to the KP equation, but taking limits and things like that. But it turns out there's some nice geometry associated to this, linked to the geometry of Grassmannians. So you get KdV type equations when you shrink the lattice in all sorts of ways. It's a sort of heavy in formulae.
You said this, but again, what is the meaning of the symbol attached to these vertices? The symbol attached to these vertices.
Okay, so you got numbers basically.
Just numbers.
Yeah, and you're computing from what's coming before and then moving outwards. And what's interesting is they seem to sort of converge to things when you put in weights and probabilities and things like that. You get sort of interesting results. So the paper says, well, this is like, and this statement occurs for these Hurtubise bilinear cases. Well, these are the Plücker relations. Well, how? Actually, Miwa seems to be associated with the orthogonal group, and then for spinors, you have similar relations due to Cartan, so called the Cartan relations. And the Kashayev and the hexagonal ones a bit strange, but they seem to actually, in the end, be associated to the symplectic group. But anyway, so this sort of these facts that they're always finding, integrable limits, KP limits, and things like that, make you think of the Sato, Siegel, Wilson, Grassmannian, which is quite a remarkable object, and it's this wonderful. Well, it starts with Sato, but Siegel and Wilson give just this beautiful exposition of the theory. So what do? Well, you start with the Hilbert space, which is L2 of the circle, and you split it into positive and negative frequency Fourier series, so H plus and H minus. And then you build a Grassmannian, which is a Grassmannian where the planes are very close to being the positive plane, H plus. So we'll do close that way, in the sense that the projection to H plus is Fredholm. And the projection to H minus is small, left deliberately vague, but things like trace class or compact or whatever suits you in the context you're working in. And the point is that there's a Fredholm index to this, and the Fredholm index is what gives you a sort of virtual dimension on the set of planes. So there's an integer there of classes. So it's in fact the sort of a natural locus for flows of the KP hierarchy. So an infinite number of differential equations. But I want to consider finite dimensions first, because there's some interesting questions. You know, these they're supposedly Plücker relations, but you're not getting all Plücker relations. So what are Plücker relations? Okay, so you've got Plücker coordinates, which is coordinates on the Grassmannian of K-planes. And of course, if you're looking at a K-plane, one way of defining it is to just give a basis. So this is my sketch of a matrix. And you take basically all the minors of size k in this. So say this one here. So then you get a k by k matrix. Take its determinant. And those are coordinates. They're obviously invariant under the choice of basis. And it'll give you an embedding of the Grassmannian into projective space. Well, that's nice, except, of course, not all elements of the exterior product are products. They're sums of products. And so which ones are sort of products on the nose? And then there's a variety of sort of more or less confusing ways of giving these Plücker relations. But the one I like is that you choose a sort of seed multi-index. So this is I0. So remember, these will be coordinates of an element of the exterior algebra. And sort of you put it at the beginning. And then you complete it, not to an index of length k, but a length first k minus 1 and second k plus 1. And then you borrow in turn an index for the longer one. So you remove it here, pop it in the end, remember a sign, sum it up, you get 0. And so these are the Plücker relations, and you can see that basically the number of terms here is going to be determined by the I0 here, which is the length of this multi-index. So their shortest ones possible have 3 terms. So they look like that. And this looks very much like the Hirota relation. So you could actually say, okay, but that's just, you know, it's a quadric. Lots of quadrics. Now, admittedly, for the lattice, you've got a bunch of them. But what about all the other Plückers? And there are theorems that exist to say that these things are, you know, the 3-term relations determine the others. Generically, you know, up to either as a set or as an ideal. But in fact, there's a nice geometric way of seeing it, which is you take this element of the exterior algebra and you restrict it to subspaces. And the test basically is, okay, in the big space, it's an element of the exterior algebra. If I restrict to this family of subspaces, does it then define a plane? In other words, is it decomposable as a product? And what happens when you decompose this, you restrict to spaces that are just built from the coordinates. So this is when you think of what happens to the relations, the longer ones Plücker just disappear, and you're just left with the 3-term relations. And then geometrically, you can see that, you know, if you've got a plane downstairs, and there's a bunch of them, but if you assure that they're compatible under restriction to even smaller, so you get lines, basically, and then you can sort of build it back. And so basically, this is telling you geometrically that these 3-term relations give you everything. And they also tell you what type of genericity you want, which is just that the intersections are transverse with the coordinate hyperplane. So it's quite nice, and you don't have to worry about multiplicities. So what about the Kashayev relations? Well, here you're looking at isotropic planes of maximal dimension, so Lagrangian subplanes, for a non-degenerate skew form on C2n. So the end planes have their Plücker coordinates, which are, again, just given as linear GLN coordinates. And then in addition to the Plücker relations, you have this constraint that the contraction with the skew form is 0. And so these are the sort of primitive elements of wedge n of C2n. And so now you can play the same game if you want to see the relations that generate everything. You restrict, but then you bear in mind, think of symplectic reduction. You restrict, then you quotient out. So you do the same thing here, choosing pairs of coordinates, sort of dual coordinates, and then play this restriction game. You have to first get the restriction for each pair, and then you have to check that the pairs are compatible, and it's the same story. If you can get down to one dimension less and everything works there, then you've got something that's determining a plane upstairs. So it's again, it makes the longer Plücker relations disappear. And here I've just written in terms of going from n to n minus 1, but in the end you go down to dimension 6. And so in dimension 6 there'll be 2 sets of Plückers. So I'm going to write the coordinates, the sort of dual under the symplectic form. So there'll be 1 and 1 star, 2 and 2 star, 3 and 3 star. So you'll get some long Plücker relations, which have 4 terms, and some short ones, which have 3. And then the isotropy gives you extra linear relations. So you combine these things, and basically you get rid of anything with a repeated index. In other words, 1 and 1 stars, you want to get rid of that in your. So you just play around with the equations. And so in the end, once you've done that, you have 1, 2, 3, 1 star, 2 star, 3 star, 1, 2 star, 3, and so on. Right? This is the notation. And once you do that, you're going to get in the ideal generated by these things, you'll get the Kashayev relations. The extra ones that occur for the hexagonal relations, the Kenyon and P-mantle, you just use the remaining terms, the things you sort of got rid of, and you get the hexahedral relations. And this is the generic condition to be Lagrangian in dimension 6. So the hexahedral relations on all coordinates symplectic 6 planes plus compatibility give you a Lagrangian subspace upstairs. So you've reduced these things to these short relations, but a bunch of them, basically, and in all of these cases. So that's the finite dimensional story. But of course, you can take a limit. The Miwa relations, it's interesting. This is where you've got, instead of n planes, isotropic Lagrangian planes, you've got isotropic n planes. So of course in C2n there are 2 families of isotropic planes. They're parameterized by pure spinners. So this purity condition is given by these Cartan relations. It's interesting that the easiest place to find them is in Cartan's original book, which is almost impossible to find in our library until I went to my wonderful colleague Nicky Cameron's office and found it, of course, sitting on his shelves. And said, "Nicky, can I?" Yeah, thank you. So you've got these Cartan relations, and the same story. They have length, and the short implies long generically. It's interesting because the calculations with spinors are actually easier. So this is, I don't know if there's a moral there. But. So we go back to the Sato-Siegel-Wilson-Grassmannian. Now, of course, for this Grassmannian, you're taking a limit. And in fact, the limit is kind of interesting because the things I'm going to consider, a lot of the functions that actually occur, so the tau functions, which I'm eventually going to discuss, they're formal series. So the things that come up in combinatorics, enumeration problems, the first question they seem to ask, oh, is this a tau function? But they're formal series, like the formal series you build for this Witten-Kontsevich, you build a generating function for the relations on the cohomology of the moduli space of curves, sum it all up, put in factors of t, divide by 2, multiply by n factorial, and you get a solution to the KdV equation. It's a formal solution. So it's the same thing here, but you can do this in everything that I'm saying can be done in a sort of formal context. And in fact, we owe a lot to Semyon, who very courageously did the sort of foundational work for this. So you've got this Grassmannian, which is a space of half-dimensional subspaces. And the new thing is you've got an infinite dimensional group that's going to be acting on the Grassmannian. It's acting on L2 of H, H, which is L2 of S1. It's just holomorphic functions from the disk to C star. So it's acting on the Hilbert space, so it's acting on the Grassmannian, basically. So if you write a sort of arbitrary power series, x, so the t's are the coefficients, z's are the coordinate on the disk, then from a base point in the Grassmannian, you'll get a family of these curves. So there's a line bundle on this Grassmannian, which is the infinite dimensional analog of the dual of the tautological bundle, so the determinants on the planes, or volume forms, if you want. And in dimension 0, you'll get a section. So this section is almost the function you want. But you have this picture, if you want, where you've got, here's your Grassmannian, and here's the got a line bundle above it, and sorry, no, not a 0 here. Anyway, so it's a line bundle. You'll get a section of this line bundle of it, but the group. So maybe this is. I'll just put gamma of W. So it's sitting inside the Grassmannian. So you've got a section over the image of gamma, but gamma is acting not only on the base, but it's also acting on the fibers. So at a point, you could just, that's in the image of the translation, you can first evaluate the section, that's good. But you can also sort of go from your base point, which is W0, and apply the group action. And then you can compare the two, and that'll be the tau function. So it's a function. And so that's what this formula is supposed to say. And then there's this sort of metaphysical statement that everything's a tau function. So if you choose the Grassmannian, that's just a sort of combinatorial shift of the coordinates in L2, you'll get Schur functions. Theta functions, well, theta functions for a Riemann surface, well, how do you do it? Well, you define your plane to be the sort of set of sections with poles only at a fixed point of a line bundle on it. There's a whole, it's this Kirchhoff method, if you want, for solving these equations. And up to sort of some normalizations that are admittedly not easy, you're getting theta functions. And like I said, in all these combinatorial things, you're finding these things. So this is not to be taken seriously, but it's, you're getting quite a lot of solutions. But you are solving this KP hierarchy. So you're flowing in an infinite number of directions at once, and each direction sort of is one equation, basically, and the compatibility will be the PDEs that you're solving and so on. So that's the thing. So the basic game here are these Hirota relations, which take a bit of getting used to. Oops. Oh, there, oh, that's a nice dot. You've got this funny symbol here, which is this infinite sequence. And so you choose a Z and shift the t parameters this way, shift the s parameters this way, multiply by this, and this, taking the residue at z equals 0 gives you this, as you can see, quadratic relation in the taus. So this is what gives you the quadratic relations. Oops. Oh, hello. So more sort of, a bit more precisely, you've got this line bundle L, and it's essentially O1 for this embedding of the, well, fermionic Fock space, but it's an infinite dimensional projective space if you want. And these will be the eventual projective coordinates. And of course, the Plücker embedding restricts O1 on P to the nk minus 1 to this sections of this tautological line bundle. But a bit more if you can manipulate the tau functions. This way, you define these quantities eta ij. Then in this, just take these quantities, you can see that it gives you exactly the Hirota relations that you'd had. So this is and they're more general ones. And, you know, not, in some ways they're well established, but they're not necessarily easy to prove. So in this game, there's also a sort of funny thing where you're thinking in some sense in terms of integrable systems. So you're thinking, well, I've got a sort of fixed point, then I'm flowing. But Plücker coordinates are defined for one point. Well, they're not really defined for one point. If you define them on the functions, they're sort of defined on the coordinates, on the whole manifold. But in any case, the flows, you can make a flow coincide with preserving the plane. And you can think of it in infinite dimensions. You're just sort of sliding the coordinates along. It's not a terribly fruitful way of thinking. And, you know, it's achieved a result of some acrobatics. But anyway, you can do this. In the end, we just stick with the flow picture. So you're starting with a fixed plane in the Grassmannian. You're taking a lattice. Remember, this is, oops, oh, pressing the wrong button here. You're taking a lattice generated, again, this funny symbol xi, you know, it was this infinite sum in the t coordinates, but you're just taking a finite number of them and you're taking their linear combinations, or z linear combinations. And you take the tau function, put a little tweak here, and the tweak is kind of interesting, but it's necessary. And you'll get something that will satisfy the Plücker relations. The how is there's again another shift here that you have to put in. So the shift is well, how would you parameterize the Plücker coordinates? Remember, they're given by elements of the exterior product. Here, the exterior product is an infinite one, but a sort of finite, if you want, finite Fredholm index when it's compared to H plus. So you can have an infinite sequence of points. Here's 0, here's -1, here's -2, and so on. And you can define a sort of element of the exterior algebra by taking basically almost all negative ones, but skipping some, and then having a few sticking out into the positive direction. So I have 2 holes here and 2 or 3. Maybe I need an extra hole. I'll just put one there. 3, I don't know, occupied sites. And so this business ends up being called a Maya diagram. And then you can build a partition by sort of looking at the amount of shifting you need to do to get from the standard widget to this one. So you'll have to take the element here and put it out, shift it by 4, and then you'll have to take the element here, and I guess shift it by 4. So I managed to write something that's completely banal, so maybe I'll do this one instead. And this one gets shifted, I guess, by 3. So you get something that looks like a partition. And so you do a little bit of a tweak. You've got a partition, and then you shift these hns of w that I've defined in terms of the tau function by basically the coordinates of those partitions. So you've got this infinite integer vector n. And then the statement is very neat. It's just that the map from the Plücker coordinates to these hn lambda of w is a ring homomorphism. So if you've got relations you've got Plücker relations here, you'll have Plücker relations there. And it uses a non-trivial application of the Hirota relations to do this, which is this widget here. But you again see it's basically a Plücker relation. And so, as I emphasize, you can prove it on a formal Grassmannian, because basically you're just taking finite combinations at a time, so you don't really need to worry about convergence. So you're doing it on formal power series, and this seems to be useful. So to go back to the Hirota, there's an extra little 1 that slipped in there in the second equation. But you're getting this solution to the Hirota equations. The Lagrangian case is amusing. So there you define a symplectic form, a skew form on H, which is just this residue of f of z times g of minus z. The 2 basis subspaces are isotropic. And you look at maximal isotropic subspaces that are commensurable with H. So again, it's Fredholm in one direction, small in the other. And you have the standard GL tau function, which now sort of is invariant under an involution. You define this thing here. And then oops, with that.
Sorry.
Yeah.
What's your integration?
Just the residue at the origin.
So whatever some
Yeah.
unit circle or something.
Yeah. Sorry.
And why minus that is a natural? It's just a choice, right? Or
Well, it's what it'll make it symplectic in the end. Skew. make it skew, basically. So I guess if you were doing we haven't really done the orthogonal case, but you'd probably there'd be no minus sign there. So the Lagrangian tau function is basically a square root of the other one. That square root is mysterious. We really can't see it. You could sort of see it in the orthogonal case, the spinors with, you're taking square roots there. But this is not orthogonal, it's skew. And so, but it's there. And developed in the paper of Hurtubise and collaborators, anyway, that sort of develops this theory. But it's the same story. You can define your discrete, these functions that are derived from this tau function. And then define the h's in the same way. And you solve the Kenyan P-mantle recurrences when you're restricting to a z cube. So you have these discrete equations. Like I said, it's a theorem that's sort of there in a lot of the papers in some ways, but it's nice to see that it's actually a very nice geometry. It is basically the thing you'd expect from a discrete Hamiltonian system. In other words, it's sort of integer lattice in the continuous system, and it works. The quadratic case is the orthogonal case. Like I said, you can do it with same story with spinors. There are tau functions there that are well defined for the dn case, and you get this basically the same results. So it's an interesting thing. I'm not sure what it implies for all these limit results in terms of there's some equation that generates them. It's also not entirely clear because the recurrences do need some initial conditions, and sort of what initial conditions you have to give given all their Plückers. Well, from the lattice point of view, it's fairly clear. From this point of view, is it some subset of the short Plücker relations or some? So that's a little bit confused. But in any case, you get solutions. You get solutions flowing in not just z cubed, but z to the whatever as large as you want. So you're seeing the full integrable system there. So I seem to have either spoken too fast or underprepared, or not prepared enough things, or so on. So maybe I'll just stop there. So thank you.
Questions, comments? I got a couple of questions. So maybe one, right now, often those Plücker relations, people consider them in context of some cluster algebras.
Yeah.
And but how is it? Is there some infinite dimensional version, right? Because you now have those starting Rosmanians, and they're like so. Is there some cluster approach to this infinite dimensional version?
I'm really the wrong person to ask, but it's a very interesting. Yeah. No. I mean, it is a question because I personally have always found cluster relations very mysterious.
And maybe then
Yeah.
another question on the finite dimensional side, right? There are all those whatever periodicities of those wide systems, right? There are relations of this Hirota type where in the end you return to the same point. There are those periodicity conjectures which were then proven with different techniques.
Mm.
Do you have some view on like periodicity phenomena in this?
So you in other words, you take your flows and you come back to the same.
They observe basically for some of those with some kind of boundary conditions, right? You said that with some kind of initial conditions and so on. So So you do your steps,
Yeah.
right? The linear calculations allow you to move, like, let's say,
Yeah.
to define some kind of discrete dynamical system, and then it has periodic solutions.
Yeah.
So,
Well, you know, there are, of course, the tau functions do include the quasi-periodic flows associated to Riemann surfaces. So maybe, you know, that's one possible out for finding them. But probably, I'm not sure it fits terribly well with the boundary condition. Are the boundary conditions also periodic, or are they?
yeah, that's okay.
Yeah. So, but you can see that you know, you'd get, you know, with the sort of planes associated to Riemann surfaces, you've got this infinite parameter of t's. It's all sort of collapsing into quasi-periodic flows around one Jacobian. So, I guess it's always an interesting thing to explore. And you know, in this, again, the solutions associated to Riemann surfaces, there's always this sort of aspect of the sort of flows for a smooth curve and then flows for a rational degeneration, which give you solitons. So again, that's a sort of interesting side. So can you get solitonic flows here?
Thank you.
Yeah.
So, Lisa has a question?
Yes, I just wondered, do your recurrence relations give rise to differential equations in some limit, as in undergraduate
yes,
differential equations courses?
Yeah.
You teach
Yeah, you look at
difference
the-
equations as well as differential equations. Is there some limit where your difference equations give rise to differential equations?
Yeah, no. If you look at the original, mostly Japanese papers, Miwa and Jimbo and company, they have these degenerations, and they're pointing out that this is why, you know, I was saying that probably you show this to them and say, oh yeah, of course. But for sort of amateurs like myself, it's kind of interesting to see the actual geometry come in. But they're very definitely, the limits are there. But what this does also is say, well, you know, somehow it should be, these cases, you know, this is should be some sort of universal scheme, which is interesting. I'm not sure. And of course, you know, everything with these discrete flows, there are issues of convergence. You know, sometimes things go wild, and that's that. But you know, that happens with you know, finite dimensional integrable systems too. So.
Well, thank you very much. Beautiful talk.
Thanks for the nice talk, Jacques. And there was a paper that came out a few months ago by Einar called Hurtubise and geometry, where it was the Hurtubise relations and Siegel-Wilson investment in the context of topological recursion. So I'm wondering, and I know you haven't used topological recursion, so is there a way to get tau functions for
Well, it's always the statement that he takes his correlators, then sort of condenses them into a function, and it's supposed to be a tau function. Yeah, Bertrand's a bit of a mystic, so he's often right. I mean, but it's sort of nailing him down. So I'm actually working on something with him and his student, well, who's going to, and basically trying to work it through and see it happen for the, but it is one of the next questions, is to, we've more or less figured out the correlators, and now we have to see if we can condense this in some rational way to, but this is basically for connections over a Riemann surface, G connections. So that's a slightly different story, but you know, in some sense, with a bit of work, you know, with this Kutchever method, you can sort of embed a lot of the things in this Grassmannian. Slightly artificially in some ways, but so yeah. And tau, it's also misleading because there are many different types of tau functions. For example, there's a tau function associated to isomonodromy problems. So it's become code for just sort of determinant of something that has parameters in it. So, yeah. Yeah. Yeah, it's just the coordinates, the Plücker, if the Plücker coordinates. You could define, there's a way of restricting the flows to basically, by the way, my friend John Harnett has quite a marvelous book with his former student on tau functions that has everything you wanted to know about this. But you take a planes, the family of planes that's sandwiched between two planes, one virtual dimension small and one virtual dimension bigger, and then things sandwiched between. You get a sort of finite dimensional sector. You can get a subgroup of gamma to act on that, and you will get things that will essentially express determinants. And in some sense, there's also the Schur functions, which occur in these as tau functions, but for very special W's. Well, in fact, it's the W's that occur from this shift process of just taking a basis. So yeah, there's lots of finite dimensional things that come out of this. Yeah.
More questions or comments? But if not, we'll thank you.
Okay.